Hey, this video is to try to help explain how to do the repeated eigenvalues problems from the MyOpenMath homework. We actually covered this prior to the global pandemic, but the problems are very difficult, so it makes sense that if you're struggling with it, then there's a reason for that. So just to get you back into the mindset here. So we're thinking about linear systems. So we've got the two equations and we've written it in matrix form. And so from that, we can form the characteristic polynomial over here. Go to a different color. Characteristic polynomial by subtracting along the diagonals lambda, multiply the diagonals and subtract the off diagonals to form our determinant, set it equal to 0 and solve, right? And so these repeated roots problems form a very special system, right? So if we think of the roots of a polynomial, these are only going to occur where you have the situation that's drawn in red here, where you just barely touch the axis, right? And so at this point, we'd say that there's a repeated root. So that would look like lambda minus 2 squared, say, right? So if we have even an epsilon above or below that, so plus a small number epsilon, then we would not have repeated roots anymore. So you might think that this is a very special circumstance when we have an exactly repeated root. And that's completely true. However, these are more important than you might think because they often form the transition state between two different behaviors. So it's important to understand where those transitions occur and the dynamics in that region is strangely more important than you might think. So in physics or something, this would be like a phase transition would occur where you would cross these two lines. So it's important to understand there's something weird happening there, but they can be important to understand. Okay, so that's the physical situation. Mathematically, so we know that when we solve these, if we have our two eigenvalues, we get our exponential solutions where we can combine the two together. But when we have just the one eigenvalue, we only get one sort of solution out of it. So in this case, we have 2 as a repeated eigenvalue, and we get just this one solution, C1 e to the lambda t times V1, right? And if we have a distinct eigenvalue, then we can form the second one and go from there. But how do we find that second solution is the big question for today. So the idea here is to add in a solution that has times t in it. And this won't always work, but very often it's a good guess. So if we guess that in, if we add in a term like that, we get a linear independent solution, and we can, as long as we can solve that, then we have our second solution. So we're just going to do the old guess and check method of differential equations. We're going to guess that it has a solution of that form, plug it in, and try to make it work. And the way we try to make it work is to solve for the d1, d2 there. Okay, so let's fast forward here down to, well, here's the review of the solution technique. So we take the one solution that we found, and then we're going to guess this solution. So we take, you notice the V1 and the lambda, those are recycled. The t is formulaic. So all of this is known except for the d part. And we're going to solve for d. For that, we just have to plug it in, plug and chug, and we'll get it down to a linear system that if we can solve it, then we found a solution. If we can't, then that means this technique doesn't work for us. All right, so then if you look back in your notes, you can see an example. But let's fast forward here to one that's actually taken from this homework problem. So your numbers will probably be slightly different, but you should be able to follow along here. So we're given a linear system. Here's our initial conditions. So this is an initial value problem. I'm first going to rewrite that in matrix form. So coefficients of x in the first column, coefficients of y in the second. And I'm defining the vector x to be x and then y, right? So we'll just have to keep that in mind. I try to be consistent with writing the vector on x when I mean that. But we'll circle back to that at the end of the problem. So we're going to proceed as usual here. We're going to subtract minus lambdas along the diagonal. That's our A lambda matrix. We'll find the determinant of that, which is the product of the diagonals minus the product of the off diagonals. which gives us this, right? Then we expand that, we get our characteristic polynomial. We look for roots of that, so that looks kind of nasty, but it turns out, so this discriminant part over here is 0, which means that this is what happens when you have a repeated root. We get plus or minus 0, right? So we don't have those two distinct roots. In fact, we just have negative 1.4, or if we want to write that in sort of fraction terms, that's minus 7/5. So we've got a repeated eigenvalue. Well, we get one solution relatively easily, or at least in the normal way, and that's just our eigenvalue in the exponent times our eigenvector. So to solve for the eigenvector, we use the definition here, a v1 equals lambda v1. I now know what the lambda is, so I filled that in. You can move this over to set up this solution set equal to 0, and then fill this in. So I get this matrix, and it turns out that minus 0.4 plus minus 1.4, we're gonna get nice a nice matrix surprisingly out of that, right? So once we fill this in, we get this A lambda matrix over here times v1 v2 equals 0 0. So you notice that these two rows are redundant. They'll always be redundant. So really, we can just take this first line here, v1 plus v2 equals 0. I can choose, there's a whole line of solutions here, so I can choose v1 whatever I want. So this tells me the same thing as v2 is negative v1. So I'm just going to set v1 to be 1. Therefore, this tells me v2 must be negative 1. And this just has to do with the fact that any vector in the direction of the eigenvector is also an eigenvector. So that's a regular way of finding the eigenvectors for a 2x2 system. And by the way, you can check this, that this really is an eigenvector by plugging it in. I should get negative 2.4 times this back for our system. All right, so that's our one solution to the system. And now comes the repeated roots problem, right? So here's our goal. We want C1 times the one solution plus C2 times the other. Once we find that and those two solutions are linearly independent, then we're done, right? That means we can write any solution of this problem down using those two solutions that we found. Okay, so we need that second solution to get all of the possible solutions. And as we saw, a good guess would be t. If we put a times t in there, we get a linearly independent solution, and that very often works. So here comes our guess, right? So this is what we wrote down in general form above, e to the lambda t, v1t plus d, and we need to find this offset d, this offset vector d. All right, so by the way, when you plug this in, you're always going to follow the same procedure here. So I'm going to do the usual math trick and do it once in general. So here's my system. Here's the definition of an eigenvector, an eigenvalue. I'm going to plug that in. So d by dt of x is over here. A x is over here, right? This is just filling in. And then we're going to do a little bit of calculus. So this is a product rule here. This is, well, that's just a derivative of an exponential times the d. Over here, the only term would be a v1. A goes with v1 here, which by the definition of an eigenvector is lambda v1. And over here, this is just e to the lambda t, which is a scalar, and then a times d. So once you do some cancellation, you can see every term has an e to the lambda t in it. We can cancel all those out. And then the two pink lines cancel out those two terms. And we're left with this remanence left, which will always be the case, right? So now we can fill in what our actual v1, lambda, a, and d are in this case, right? So we're going to solve for the d. But so this is always going to be what you get down to. So when you're working this problem, feel free to skip to this step as long as you know where this came from. All right, so then a minus lambda 1, well, that's actually the same matrix we formed earlier. That's this, right? A minus lambda. So that turns out to be strangely nice. 1, 1, minus 1, minus 1. Times d1, d2, that's what we're trying to solve for, equals, and then this is my eigenvector. All right, so then we have to solve this for d. Once again, this is going to be redundant, so I get d2 equals 1 minus d1, and then let's just choose d1 to be 1, therefore d2 has to be 0, right? So like these two rows are always going to be redundant as well, so we have an arbitrary choice to make, so choose whatever one's easy. You just need to find one solution to this. There's going to be an infinite amount. So this gives us our second solution. E to the lambda t, t v1 plus d, right? Once we find the d, which in this case is just 1, 0, we've found the general solution. All right, so here's our general solution. It's the combination of the repeated root solution and then the original solution. And because we're given initial conditions way back at the top, we were told, hopefully I'm not making you dizzy here, we were told x0 is 0, y0 is 1. Well, then let's find those coefficients C1 and C2 that give us that. So when you plug in t equals 0, you're going to get pretty simple because e to the 0 is 1. This t of 0 is going to give you 0, so you get C1v1 plus C2d, which gives us this linear system. It's our last linear system, I promise. And so what are the solutions to that? Well, so I could just kind of stare at this for a minute and say, well, I need to make 0, so let's make this minus 1 plus 1. So multiply the first column by negative 1, and then the second column by 1, and that'll give me my 0, 1. Maybe you need to write these down or plot the two lines and find the intersections. But however you want to do it, you can find that this is a particular combination of these columns that gives you 0, 1. So I fill that in and I get my particular solution that's correct for my initial conditions. And this is still written in vector form. So we need to remember that our vector x, we define that as the x species first and then the y species. So the equation for x is just the first row. So that's the first row, and the y would be the second row. So if you extract that out, you get e to the minus 7/5 t times 1 plus t times 1 minus 7/5 plus 1 e to the minus 7/5. You get some cancellations, and I get just t e to the minus 7/5 t. And then on the second row, this is what you get. And so, for this particular choice of constants, then that's what you get for the solution in my open math. So you can tell that this, like I said, these are difficult problems, or at least they're lengthy problems. So hopefully this video has been helpful.